a really nice theme of trying to make random quantum circuit experiments more verifiable by adding structure to the experiment. So we have Dominik Hangleiter here from the University of Maryland. Will tell us more.
Awesome. Thanks very much, Bill, for inviting me to give the talk here. I'm really excited to be telling you all about this research, which I've been doing together with Michael Gullens, also at Maryland. And it's really following the theme that Scott introduced this morning, and actually already introduced last year at this same conference. Those of you who were here will remember, it's the question whether there's a quantum advantage which is scalable, verifiable, and NISKY. Okay, and I'm going to talk about the same set of experiments, namely these random circuit samplings, or as I call them, quantum random sampling experiments. And I'm going to ask the question whether we can make them somewhat more verifiable. I'm not going to claim that in the end there will be a fully verified quantum advantage, but maybe we can, do little steps towards that goal. Okay, and before I, dive into the talk, I want to already give you the highlights and the sort of tell you what you're going to be expecting. So I'll introduce a new scheme, a new setting of quantum random sampling, in which instead of doing quantum random sampling on a single copy of a quantum system, we're now going to copy that random circuit on a second copy, and then we're going to do a Bell measurement. That's basically the setting. And what I'm hoping to show you today is that in this setting, we have hardness of sampling, very similar as in random circuit sampling. We also have structured distributions on which we can do property tests, some of which are efficient, some of which are inefficient. If you're a physicist, I'm a physicist, if you're a physicist, you can do efficient fidelity estimation in the same setting in which cross-entropy benchmarking works in these circuits. If you're a computer scientist, well, I have a couple of proposals for you, and these are by no means complete and fully thought through, but they're proposals that I invite all of you to think about and that I think would be really exciting to make some progress on. So the first is a quantum advantage test that maybe is a little bit more difficult to spoof than just cross-entropy benchmarking. And the second is the suggestion that maybe Bell sampling might actually be more noise robust in a scalable sense than random circuit sampling. Okay, so the plan for the talk is to do a brief recap of quantum random sampling. Then I'll introduce the Bell sampling protocol. I'll talk about noisy Bell sampling. I'll briefly talk about Bell sampling in experiments and the question of scalability, and then give you an outlook and some open questions. And throughout this talk, I will invite you to have, raise questions, and I will myself raise more questions than I have answers. And
Sorry, are you making actually sure that the final state that you're measuring is a Bell state, or you're just testing that it is a Bell state out of a random?
Let's get to that in a moment. Okay, I'll go into more detail. Right. Okay. Good. So let's start with a brief recap of quantum random sampling in the noises case. Okay. In the noises case, what we have is we have a random quantum circuit, which we draw, classically from some family. Say we draw individual random gates, we put them on some architecture, and then the task is to sample from the output distribution, which is just this computational basis output distribution. Okay, for example, I will go through this reasonably quickly. We have the circuits which were chosen in the Google experiment, where there's some fixed two-qubit gates, depending on the architecture, in the staggered pattern that Scott was explaining. And then there's certain random single-qubit gates. And then you repeat this layer by layer, and in the end, you sample from the output distribution. Okay, for these types of circuits, we have essentially two tasks that we have the sampling task that we can consider, and we have two sorts of hardness arguments for the sampling task. The first hardness argument is due to Bremner, Joseph Shepard, and Scott Aronson, Alex Arkhipov, which basically is that assuming some complexity-theoretic conjectures related to the output distribution, the simulability of the output distribution, and then the famous polynomial hierarchy collapse, there is no efficient classical algorithm that approximately samples from that distribution. within a constant total variation distance. The second type of task that you can consider is just, instead of sampling, you can just consider the task of producing a couple of outcomes which have an average probability with respect to the ideal circuit, which is larger than 2 to the n. That's essentially this cross-entropy benchmarking test that Scott was talking about. Okay, so let's take a look at the distribution. The distribution in quantum random sampling is very unstructured. It's very close to the uniform distribution if you just look at the individual probability. All of them are roughly on the same order of magnitude as the uniform distribution, which is this red dotted line here. If you draw the probabilities in a histogram, you see this exponential decay. So most of the probabilities are on the order of the uniform distribution or even smaller than that. Okay, let me now briefly talk about verifiability of quantum random sampling. Well, the first observation that you can make is that if you want to actually verify total variation distance, this very stringent task that we were setting in the complexity argument, then this is something that will require exponentially many samples. And the reason for that is very simple. The largest probability is just exponentially small. And so to resolve that, I will just need exponentially many samples. Right. So now we can look at weaker tasks, such as cross-entropy benchmarking. Here, as I said before, which in this X, yes?
Isn't the largest probability even smaller than that? Like more like n over 2 to the n?
Yeah, this is like the rigorous bound that we can prove for designs.
Right,
yeah.
fine,
But if you have exponentially distributed probability, it's much smaller. Right. Then the other task that we can consider is this cross-entropy benchmarking test. Here we just get samples from the distribution. We calculate the average ideal probability corresponding to those samples. If your circuit U here is sufficiently random, anti-concentrates or forms a 2 design or so, then we have exactly this property that Scott was already telling you, that if you have the ideal circuit, the cross-entropy benchmark is 1. If you have a uniformly random samples, then the cross-entropy benchmark is exponentially small. Good. So there are two nice things about this cross-entropy benchmark. The first is it's sample efficient. You can efficiently estimate it from a small number of experimental samples. So you don't actually need to run your quantum device for months. You can just run it for a few hours or so. The second is that here, the cross-entropy benchmark actually gives us a distinguisher against the uniform distribution. That's essentially what this property is telling you, right? For the ideal distribution, you have a high score. For the uniform distribution, you have a low score. You can also look at it from a complexity perspective and make the claim that it's hard to achieve a high score on this benchmark classically. That's basically what the Google experiment is based on. Like the supremacy is claimed is based on this complexity theoretic effect. Okay. Now, if we look at efficient tests, computationally and sample efficient tests, then we actually believe that we can't even efficiently distinguish samples from a random circuit from the uniform distribution. And then what I'm going to talk about, this property will be relaxed, and we will actually be able to distinguish the samples from Bell sampling from the uniform distribution. Any questions so far? Oh, great. Awesome. Yeah, Abhinav.
What property was that last result based on?
I wouldn't say it's a proven result. It's more a belief that we have. Yeah, I guess it's basically, that's all I want to say. We really believe that we can't efficiently distinguish samples from random circuit samples from the uniform distribution.
And that belief breaks down in Bell sampling.
That belief breaks down in Bell sampling. We can provably distinguish it efficiently from uniform. Good. Okay, let's talk about Bell sampling. In Bell sampling, instead of taking a single copy, now we will take 2 copies. Okay. We take the same random circuit, we take 2 copies, and we perform a Bell measurement. The task is to sample from the output distribution. So let's lose a couple of words on the output distribution. So the output distribution I can write as follows. We have C tensor C applied to some fiducial initial state, and then we compute the overlap with the Bell state. The Bell state, so the output string is now a 2n bit string. Okay, the Bell state I just write as the 0, 0 plus 1, 1 Bell state and apply a Pauli on one of the systems. And I will label the Paulis with the 0, 0, 0, 1, 1, 0, 1, 1 symplectic representation. Right? So The 1, Pauli, that's going to be important later, is the Y Pauli. That corresponds to the singlet state. The 0, 0, 1, 0, and 0, 1 Paulis are Zx and that. Okay. That's the Bell sampling distribution. The first point I want to make, Bell sampling is actually realistic in near-term experiments, even I would say in today's experiments. In particular, in 2 architectures, but there may be more. One is Rydberg atoms and optical tweezers. So let's say, okay, what makes Bell sampling difficult in near-term experiments? It's, of course, the Bell measurement between the 2 systems, right? So if you have a local architecture, then you need to do many swaps in order to do the Bell measurement. But in some architectures in which you have long-range interactions, such as Rydberg atoms or ion traps, you can just do this Bell measurement in a single layer of a circuit. Okay, so that's good. It's still NISQI. The second property I want to briefly go through is that Bell sampling is still hard. We can still run the same hardness argument that we can run for single copy random circuit sampling for Bell sampling. Okay, let me briefly run you through the properties that we need to check. The first property is hiding, that the outcomes of the Bell sampling are interchangeable with the distribution of random circuits. It's a little bit tricky here, because now we have 2 systems, we have this Pauli in between. But it turns out that if the distribution over random circuits is invariant over roots of Pauli gates at the end, then we have this hiding property. The second thing we should check is approximate average case hardness of computing the probability. In particular, well, we can't prove it, but we have evidence for it. Can look at worst case approximate hardness, average case near exact hardness, and anti-concentration. Worst case approximate hardness holds, as we show, because we can embed the gap of an arbitrary Boolean function using universal quantum circuits. Average case near exact hardness just holds by standard arguments that we have by now for any continuous gate set. And then anti-concentration is a little bit more tricky because now we have 2 copies. Turns out we need 4th moments. And so it holds if you have a unitary 4 design. By result of Harrow and Meraban, we get unitary 4 designs in depth, which scales as n to the 1 over the dimension of the system. And so we also have examples for random circuits, which anti-concentrate in Bell sampling.
Can you say again, what is the benefit of doing Bell sampling as opposed to just measuring in the computational basis?
That's coming in a moment.
Oh.
Great.
I thought I missed it, sorry.
No, I haven't gotten there yet. Good. The first question here I have is, well, for single copy random circuits, we know that they anti-concentrate already in logarithmic depth. It's not clear if this is the case for Bell sampling, but, you know, it's a very reasonable thing to believe that 4th moments, or maybe even all moments, I think Michael has some evidence that even all moments anti-concentrate in logarithmic depth even. Okay, good. So now let's come to the benefits of Bell sampling, which is that the distribution has structure. So in a sense, this is precisely answering, well, a little part of the question that Scott raised in his previous talk. Okay, let's look at the Bell sampling distribution. What structure do we have? And I will explain this in detail in a moment. The first structure that we have is that it's supported on what I call the symmetric subspace. And I will tell you in a moment what that means. The second is that the outcomes have some correlations, and we will also see what exact correlations they will have. The third is that the support of the Bell sampling distribution is pretty large, actually full in, and that corresponds to what we call the stabilizer dimension. And the fourth is that it's still anti-concentrated on the symmetric subspace. So it still satisfies this anti-concentration property, which is then relevant for cross-entropy benchmarking and related questions. Okay, so if you go back to our picture before, we still have a distribution which looks a little bit like the random circuit sampling distribution, except that for some outcomes, so say the outcomes in the anti-symmetric subspace, we now know that the amplitudes are 0. Good. Okay, so let's go through these properties one by one. And in the process of doing that, we will also see how we get efficient and some inefficient tests for the properties. Good. First property, the support on the symmetric subspace. So to explain why that holds, I'll need the swap operator. So the 2-qubit swap operator I can express in the Bell basis as just the sum of the projectors with Pauli's 0, 0, 1, 0, 0, 1 minus the singlet projector, because that's the unique antisymmetric state for 2 qubits. Okay. Then the global swap operator is just the product of all local swap operators. Okay, what can we do with that? We can do a swap test. Great. So if we want to compute the purity of a quantum state, we can just express this in terms of the swap operator on 2 copies of that quantum state. And that's exactly what we're going to do. And what we see here is that this swap operator we can express in the Bell basis as just as a sum over all outcomes. And then -1 of the outcome is in the antisymmetric subspace with an odd number of 1, 1 outcomes. I call that the Y parity of the outcome. And +1 if the outcome is in the symmetric subspace. Okay, good. So in particular, if we have a pure state, we know that the purity is 1. Great. So for any state, actually, not just random circuits, for any state, the Bell samples will be supported on the symmetric subspace. Awesome. And I already gave you an efficient test, right? Because here we just sample from the Bell distribution. If we just sample from the Bell distribution, we compute the Y parity of the outcomes and we average them, we'll just get an estimate of the purity of the quantum state. Okay, in particular, if you have a pure quantum state and if you see an antisymmetric outcome, you already know that the state was not pure. Okay, are you happy with this? Questions? Great, okay. Let's go to the next property, namely correlation.
Sorry. This test that you're saying is about the classical samples, or if you had the quantum state and measured it?
This is about the classical samples,
okay.
Right? So this is about a property of the ideal output distribution of Bell sampling. I will get to noisy Bell samples in a moment.
Is that a typo? Because it should be S2 in that equation.
No, it should be the global S.
The global S is defined as a Hilbert space, or what is that?
Exactly. I have a state on n qubits. Rho is a state on n qubits, and I express now the big S in terms of the little s's, and then I get this property.
Okay, got it. Makes sense. Thank you.
And sorry, so and suppose that all 4 properties that you listed, hold. Is your argument going to be that helps with verifiability in some way?
Yeah.
All right. Yeah, that's it. But that's coming later.
That's coming in a moment.
All right.
I mean, the first sort of verifiability we already see here, right? The swap test gives us verification of at least this property, the support property. Okay, now we can do that swap test on subsystems. Because the swap operator is just a product of the local swap operators, we can just do it on subsystems as well, right? So if I now just look at the substrings, I can compute an estimate of the subsystem purity. So I take some subsystem of my qubits, I take the substring of the outcomes that I get from Bell sampling, I can compute an estimate of the subsystem purity. But we know something about the entanglement structure of quantum states. In particular, we know that the maximal entanglement we can in principle get is this triangle here, right? It's just the maximally mixed state on the subsystem, which is just given by the dimension of the subsystem, the any 2 entanglement entropy. Okay, but now if I have restricted circuits, say circuits which are restricted in depth, at some point, the entanglement entropy is not going to be dominated by the size of the subsystem anymore, but just the depth of the circuit, right? Because with low depth circuit, I can generate only so much entanglement. So this gives me a test which distinguishes circuits with low depth from, say, circuits with high depth. If I want to make it a little bit more fine-grained, rather than just comparing maximal entanglement against what I see in the experiment, I can also look at average entanglement properties. In particular, we can compute average entanglement properties for certain ensembles of state. Famously, they're called Page curves. Page already in the 90s computed that for H-random states. And it's something that looks, it lies underneath here. It's a little bit curved. There's a little correction here at half cuts.
Please. Can you remind me what you're testing for the subsystem?
What I'm testing for the subsystem is the purity of the subsystem. Okay, the purity of a subsystem is a measure of entanglement of the quantum state. So if I have a random circuit, I can compute, well, we don't have it yet. This is going to be one of the questions. I can hopefully compute entanglement properties of random quantum states on subsystems of a certain size, and then compare.
What does that mean? Is that are you hoping or saying that this you're going to actually be able to compute this efficiently, or?
I'm hoping that we can compute it efficiently, yes.
And what measure of entanglement are you using?
The Renyi-2 entanglement measure. So the logarithm of the purity of the subsystems. And I'm hoping that we can compute that with, say, statistical mechanics models on random subsystems. Okay, but even in the absence of an exact expression for the average entanglement, if we can estimate this precisely, we can still distinguish the case, like different cases here, right? If we see an entanglement that's pretty large up here, then we know, like an entanglement entropy that's pretty large, then we know that the circuit must have a certain depth, for example. Good. Great. Okay, so this also gives me an efficient test, which I call subsystem swap test. Okay, and about efficiency, we will have to talk because the values that I actually get will be exponentially small in the size of the subsystem or the depth of the circuit. So here, there's a question of sample efficiency coming out. But at least if I look at small size subsystems or very large size subsystems, the value of the entanglement is not exponentially small in the system size. And so I can efficiently estimate that or distinguish at least from very small values.
When you say efficiently, you mean sample efficiency?
I mean sample efficiency and, okay, computational efficiency is not a problem here because just what I'm doing is I'm computing the Y parity of the substring corresponding to the subsystem. So here it's really a question of sample efficiency. Good. Okay, so here's the question. What do these average entanglement properties actually look like for interesting circuit ensembles? Say restricted depth, random, 2 local unitaries. What do the average entanglement properties look like?
That's fine.
Okay, good. Let me continue with my next property and test, which I call stabilizer dimension, and you'll see in a moment why that's the case, and a related magic test. Okay. So this test is based on the observation that I can just rewrite the expression for the output probabilities in terms of an overlap with my state and the complex conjugate of the state with the Pauli matrix corresponding to an outcome. Okay. Then we know that if we have a stabilizer state, so if C is a Clifford circuit, then the distribution PC of R is actually supported essentially up to a shift on the stabilizer of S. And what do I mean by the stabilizer of S? I mean the outcome strings corresponding to Pauli's in the stabilizer of S. Okay, so we have an exponentially small support, right? The stabilizer of S is 2 to the n large. The outcome space is 4 to the n large, so we have exponentially small support for stabilizer states. Good. So now what if I add T gates to my circuit? Well, the support increases, of course, until I get maximal support on the symmetric subspace. In particular, I can write this C bar operator just as a sum from some subgroup of the Pauli group over Pauli from some subgroup of the Pauli group, sigma L, times a projector onto another subgroup of the Pauli group, and some shift, which is related to the complex conjugate. Okay, so the dimension of this L subgroup here tells me something about the magic in my quantum state. In particular, I think William called this the stabilizer dimension in their recent paper. The dimension of this is bounded, I think, by 2t. I don't want to lie about the factor of 2. I think it's 2t. Great, so this is a measure of magic. So we can distinguish states which are stabilizer states from states which have a large number of T gates. In fact, we can even learn a Clifford plus T circuit with TT gates from n log n many Bell samples, and then order 2 to the T many additional measurements on some other quantum state. Okay, and this also gives us a magic test. which is efficient because we can just estimate it from order n log n many Bell samples. What you do is you just take differences between the Bell samples to eliminate this k dependence here essentially, and then you look at the dimension of the subgroup generated by those differences. Okay, so that tells us essentially that the Bell distribution, if you have a large number of T-gates, has a reasonably large support in the symmetric subspace. The question is, though, well, I gave you an upper bound, but maybe it's actually true that the dimension is roughly the same as 2T for random circuits. I don't know. I don't have a good intuition, but that might be the case. Yes?
Maybe taking it back, but I don't understand. So, first of all, if I ignore the structure of your circuit and
Yes.
I just look at the state,
Yes.
and I want to test whether it's a stabilizer state or a different state
Yes.
that requires a lot of T-gates.
Right.
Are you saying that there is a measurement that distinguishes between
Yes.
the two?
That was known before what we did.
Yeah,
Like,
so,
that was
what's
known
the
before.
measurement?
So the measurement is just the Bell measurement. So here I'm just,
But if it's I don't have a division to two parts. So how do I do that? How do I measure?
What do you mean you don't have a division?
So suppose I just give you a state of n qubits.
Yeah.
And I want you to measure whether it's a stabilizer state or a state that requires a lot of T-gate.
From a single copy.
I mean, I'm giving you many copies, but I don't give you. I give you a single copy, you measure, then I give you another copy. You cannot entangle them.
If I can't entangle them, I'm not sure if you can do it efficiently. I mean, these experts correct me if I'm wrong. But I don't think you
No,
can
this
do
is
it
a
efficiently.
Okay. Yeah.
So you really need the two copies, I think. Good. Okay. So let's recap again. So we looked at three properties of the Bell distribution: support on the symmetric subspace, large stabilizer dimension, and correlations in the outcome corresponding to the entanglement properties of the underlying quantum state. I also gave you computationally efficient in the subsystem swap test, maybe sample inefficient tests for these properties.
Sorry, the test that you just talked about, wouldn't that only be non-trivial for like random circuits that are mostly stabilizer and that have just a small number of T-gates?
Yes. Yes, it's just a sanity check.
All right, fine.
Yes. Okay, and then we will probably still need the XCB test later. What that tests is basically that the distribution has the right heavy outcomes. That's an inefficient test, but that will still work because of the anti-concentration properties of our circuit ensemble. Okay. Immediately, these tests give us state distinguishers. Right? In particular, the global swap test distinguishes against the globally uniform distribution. Right? Because the globally uniform distribution will have odd wide parity outcomes. The magic test will distinguish from output distributions, which are generated by Clifford circuits or circuits with a small number of T-gates.
Sorry.
Yes.
Is it correct? I would imagine that if instead you had two classical, you were sampling from two identical classical distributions or classical circuits. And then you did, correlate,
Yeah, I wouldn't know how to do these things.
That would not give this, right?
Yes.
It has to do with
It really has to do,
it is the reduced density matrix.
Exactly. It's really the reduced density matrix that you need. For example, for the subsystem swap test,
Or
for the
even,
magic
even
test,
the global swap test.
even the global swap test, yes.
Yeah.
Yes. Because you don't have the support constraint if you just have single copy samples, right? Single copy samples would just be supported on the entire Hilbert space, roughly.
Sorry. What I was saying was that if you're comparing between these two noisy random circuits versus two classical probabilistic circuits, identical,
Yes.
Similar, Bell-like test there. It would act very differently.
I think so, yes. Yeah, I think so, yeah. Of course, if you just had a reversible classical circuit, that will still give you a score 1, right? But if you have probabilities in there, you won't get a score.
And all like these distinctions, I guess, is mostly like specific types of quantum circuits. You're not claiming anything about classical circuits yet?
At the moment, I'm not claiming anything about classical algorithms.
Okay.
I'm just claiming something about classical distributions, right? So classical distributions which are generated by quantum circuits with few Clifford gates. Classical distributions which are uniform, say, on the symmetric subspace. Good. Okay. Like one question that you can ask here is how actually does a test score on one of those tests translate into total variation distance lower bounds between the two distributions that I'm comparing. Sorry. Okay, questions about this? No? Great. Then let me get to noisy bell sampling. And this is where it's going to get interesting and where I hope you apologize that I proceed hermeneutically. I'm not going to give you an answer. I'm going to give you a lot of questions, and I'm going to sort of hopefully introduce you to the subtleties of this. And so to start out, let's briefly recap what happens in the single copy quantum random sampling case in noisy. So here we face now a tricky thing, right? We have on the one hand a noisy quantum device. That noisy quantum device has exponentially decaying fidelity. On the other hand, we have some classical algorithm which has exponential computational costs. So we have two exponentials which are somehow fighting each other. And this is where everything becomes really subtle and tricky, as we've already heard in the discussions of the previous slide. Let's look at, for example, the cross-entropy benchmarking score. And what does the quantum device do on that score? In the regime of low local noise, call this the 1/n noise regime, we know that the noisy quantum device XCB score scales exponentially in the size of the circuit, which essentially is now going to be exponentially in the depth of the circuit, right? Because we scale the noise as 1/n. In that regime, we also know that the XCB score relates to the fidelity of the underlying quantum state. That's something that Abhinav will talk, I think, more about later this afternoon. On the other side, we have classical algorithms. There we know actually an efficient classical spoofer in this, in the same regime somehow, in the sense that Shungao and others a couple of years ago gave an algorithm which achieves a score which scales also exponentially in the depth on the cross-entropy benchmark. So here the situation becomes really intricate, right? You have two exponential decays which are somehow the same, and now you're trying to compare them. That's noisy. That's all I'm going to say for the moment about noisy quantum random sampling. Let's see what happens in the Bell sampling case. So how well can a noisy quantum device, or on the other hand, an efficient classical algorithm, do on those tests that I was presenting to you until now? Okay, noisy Bell sampling. Well, the first thing to notice is that the cross-entropy benchmark, in some sense, has similar properties, right? We still have anti-concentration. And so we expect that the properties of the cross-entropy benchmark will be the same, right? If you have certain types of noise on your quantum state, the decay will be very similar in the cross-entropy benchmark. How exactly? I don't know. This is something to be explored. How exactly does the cross-entropy benchmark decay in different noise regimes with different noise models? Okay, now let's consider the swap tests. This is where things become interesting, and now let's start to make some noise assumptions. Right? We need to start modeling our device to say anything about what the noisy quantum device can do. The noise assumptions that I want to make is the white noise approximation, what we call the white noise approximation, which is basically that the noisy quantum state is just a linear combination of the ideal quantum state and the maximally mixed state. This is basically an assumption that was used in the Google experiment, and that we have some evidence for that it holds in this regime of low noise. Picture, yes, here's the noise, right? So when I have a circuit which has local noise after each 2-qubit gate with strength epsilon, if that epsilon is smaller than 1/n roughly, then I think we believe that the white noise approximation should hold. The other assumption that I want to make for the moment is that the measurement is actually ideal, so that we don't have any noise in the measurement. Good. So what happens? Okay, remember our page curves, how the entanglement behaves as a function of the subsystem size. Now we have two states, right? We have the ideal pure state, and then we have the maximally mixed state on the other hand. If we look at how the swap test behaves for the maximally mixed state, you can see this large discrepancy, right? The maximally mixed state, subsystem purity just goes up straight, up to 1/2 to the n, right? Because any subsystem that I take of the maximally mixed state will be maximally mixed. Good. So here I actually have a way of distinguishing these two cases in which I can be, right? In particular, if I look at the purity, the maximally mixed state at very large subsystems will have very large entropy, will have very small purity. Sorry. Okay, if I have a noise strength of eta, that just means that the purity decays linearly in eta, essentially. Okay, and then I can play the game for smaller size subsystem as well, and I will see that the purity again decays somehow in eta. Okay. I don't know very much about what the magic test is going to do in the presence of noise, because of course that's also going to be very, very sensitive to this type of noise, right? Because I increase the support on the entire space. So the magic test, if I just run it naively, will just give me, a large number for the magic, even though I actually have a maximally mixed sum. Yes.
To go back to the question you asked earlier,
Yes.
I'm not sure whether an answer to this is no.
Which question?
Okay, so for the same test that you proposed, we don't know of a TVD lower bound. Do we? Like when we compute this purity, and
We don't know against what?
against the inequality.
We don't know exactly. We don't know a TBD lower bound. That was the question I was asking. Yes.
You asked that. Okay. So we don't know the answer. But if we do assume that there's like white noise, then we do obtain some bound on what we measure.
Yes.
Is that right?
I don't know.
So intuitively, in terms of the resilience to noise of the magic test, you would expect, I'm really throwing, but you would expect a behavior that's similar to what the swap test is like. That's exponentially decaying, right?
Probably,
It's,
yes. I think so. Good. Okay. So now, that's all I wanted to say about what the values of the various tests are going to be in the presence of noise. But there's another interesting thing to be noted about Bell sampling in the presence of noise, namely that we can also use that structure to detect errors. And in that sense, Bell sampling, I think of it as a nice intermediate scheme between the single copy case and the fully fault-tolerant case, where we can detect all errors, hopefully. In the Bell sampling, we can detect some errors, right? So in particular, if we see an outcome which has an anti-symmetric Y parity, then we know that it can't come from the correct distribution, and we can say, well, this outcome an error has to have happened in order for this outcome to be produced. And we can play the same game for large size subsystems, right? If I take like an outcome and I look at all subsystems of size n-1, in the white noise approximation, I know that every error is equally likely. So if I look at all subsystems of an outcome string, then I know roughly what sort of fraction of odd Y parity outcomes I should expect. And I can use that to detect errors probabilistically, probably. And I can play that game for large constant size subsystems. Well, n- constant size subsystems. And in each step, I'm going to get some sort of error reduction, right? Roughly on the anti-symmetric test, I'm going to get a factor of 2 or so on the errors, and so on with decreasing size subsystems. The question is, what actually is going to be the error suppression if I continue this for a constant number? I haven't computed it yet, but it should be possible. Well, then, of course, the other question is what happens if I have different noise models, right? In these arguments, I've assumed white noise, that all errors are equally likely, and nice, that the measurement is ideal. Of course, this is maybe not a very realistic setting in actual experiments. So the question is, what happens to these error detection properties if you have errors that behave a little bit differently, or even if you have errors on the measurement, which is, of course, the ultimate question here in the Bell sampling case. What happens if you have errors on the measurement? Okay. Now let's look at classical algorithms. What do we know about classical algorithms? Well, okay, we already said for the magic test, uniform samples will give me a high score. So here I can just sample uniformly and get a high score. So this is not going to be a test that's going to be hard to spoof for a classical algorithm. For the subsystem swap test, the situation becomes a little bit more intricate, right? On the one hand, Clifford circuits generate very high entanglement. On the other hand, maybe if I can compute the exact average entanglement properties, then I can might still be able to distinguish my circuit ensemble from random Clifford circuits. The big question, I think, to me is whether the spoofing algorithm by Gao and others will still work. Right? So the spoofing algorithm there, the idea was, well, you have a noisy circuit that essentially deletes some edges in my tensor network. So why don't I just judiciously select certain edges in the tensor network so that my simulation becomes easier, and then simulate and, hopefully get a high score on the cross-entropy benchmark. Turns out they got a reasonably high score, right? And a score which only decays exponentially in the depth. Well, this cut here can be detected by our swap test, right? If I know where Shun cut his tensor network, then I will be able to run my swap test on exactly that partition of the circuit and realize, well, there was a pure state here. So from the samples of Shun, I can actually tell him, well, no, you actually ran this circuit in bipartition and it was pure along this cut. Now, if you look at an adversarial scenario where Shun doesn't tell me where he actually made the cut, then things become more complicated, right? Because then I might have to maximize over large size subsystems, and this maximization will become difficult. So one idea for a test could be you just maximize the purity over large size subsystems or half cuts. Another idea is you can compare the purity to the average purity. It's not really set in stone what exactly a good test that would distinguish samples against an adversarial spoofing algorithm could be. On the other hand, we also know that the classical algorithm can also use the error correction, right? That's, of course, an exponential cost for the classical algorithm, but they can, in principle, pay that cost and, produce samples which are compatible with my tests. The question is, how does that sort of error correction actually fare if my samples didn't come from, say, a mixture between the ideal distribution and the uniform distribution, but a distribution which was generated, say, by a circuit like this, which maybe has something to do with the ideal distribution, but not really. Maybe in the one case, the error detection works much better than in the other case, because the sort of errors that I see might be very different in type. Then the other question you can ask, well, okay, now you've added a lot of structure to the distribution. Does scoring a high score on the cross-entropy benchmark maybe become easier because of that? Maybe there's, maybe it's just there's a trivial way to score a score on the cross-entropy benchmark, which is bounded away from 0 now, because I have the structure. Maybe just sampling from random Clifford circuits will already score reasonably high because the correlations in the distribution are correct. I like to compare this to the situation in boson sampling. In boson sampling, we have efficient state distinguishers. In particular, we have state distinguishers from the uniform distribution or from distinguishable bosons. But we don't really have a notion of a cross-entropy benchmark because, one, we don't know what the ideal score is. And two, we don't know what actually the hard score is, right? Because even if I just produce samples from the uniform distribution, in boson sampling, I will, have a rough idea of the size of the probabilities.
Wait, what?
Sorry, not the uniform, distinguishable boson distribution.
Yeah.
I will already get roughly an idea of, how the distribution.
Wait, are there really two separate problems here? I just thought of it as one problem. That sort of we don't know what is the benchmark. That once you exceed it, then you're doing something classically hard.
Yeah, I think. Okay, it's a question. Yes, I like to divide the problem into the statistical problem, right? Where the question is, what's the ideal score, what's the fully noisy score, and then the computational problem, which is, how high can you actually score with a Casper? Okay. So here's a proposed quantum advantage test. Well, we'll still probably need the cross-entropy benchmark because, as I told you, the test that I proposed individually will be spoofable relatively easily. But maybe in conjunction with the cross-entropy benchmark, there's going to be I call it proposition, a hardness conjecture that simultaneously achieving a good score on all of those tests is maybe harder than individually on the cross-entropy benchmark. Because at least, say, the Gao algorithm, we can detect with the swap test in principle. Okay, and there's a varying scale of efficiency versus inefficiency on those tests. Okay, but then you can also ask the question, well, do the new tests actually add to XCB? Well, maybe everything that I was able to see with XCB, I can still see in the new test just with XCB. Maybe the swap tests don't actually help me. I don't think that's very likely because intuitively they test for very different properties, right? XCB tests for heaviness of the outcomes, magic tests for flatness of the distribution, the entanglement test for the structure of the correlations in my distribution. Well, then the other, German we say Gretchenfrage, is of course what's a good score on these tests, say the magic test. What is a score that we, in conjunction with XCB would think is classically intractable? And there's going to be a compromise that we saw already for the subsystem swap test, right, where maybe I have to optimize over different subsystems in terms of efficiency and classical intractability. Questions on this? Okay, but even if you, don't believe all of this, I think Bell sampling has a virtue, namely, now I stand in front of my slides, has a virtue, namely, if you're an experimentalist, you might be very willing to believe those noise conjectures, right? You might be very willing, I think the Google people are very willing to believe the white noise conjecture. You might be very willing to say that your measurements, well, maybe they're not perfect, but they're nearly perfect. And then in that case, you actually get an advantage. Because we know that cross-entropy benchmarking is an estimator of the quantum fidelity. That's actually one of the main uses for people in physics to use cross-entropy benchmarking, and why it's spread a little bit also beyond the random circuit sampling community. It's actually a way to measure the many-body fidelity in systems which are what they call chaotic. But it's an inefficient estimator. With Bell sampling, we have an efficient estimator. Okay, and Abhinav will talk about this. With Bell sampling, we have an efficient estimator because the purity in the presence of those noise assumptions give us an efficient estimator of fidelity in the white noise regime. Right? How do I see that? Well, if you have some noise parameter here in the white noise approximation, then both the purity and the fidelity of my quantum state I can just express in terms of that parameter. And so I can estimate the parameter from the purity and then estimate the fidelity from that. And then, of course, the same holds for the entanglement properties and everything else. Good. Okay, let me say a little bit about the question of scalability, or what you might call the constant noise regime.
Sorry, trying to simplify what you just said. You're saying that under the assumption of measurement, there's no noise in the measurement. And what was the other assumption?
The other assumption was this white noise assumption or low noise assumption.
So let's assume these two assumptions. You're saying that this is a test of advantage that would be efficiently verifiable. That's what you're saying?
No, I'm just saying that this is a test of, this is a way that I can actually measure the physical fidelity of the quantum state. So before, okay, let's go back to the slide before. Right, here I was talking about an advantage test. Right, here I was talking about, we have these various tests, maybe scoring a higher score on those tests actually is something that's classically intractable. Now I went away from being a computer scientist to being a physicist, and ask, well, you have all of your data. I'm not adversarial against my device. I think I sort of know how the device is going to behave, what errors it's going to have. I just want to understand how well I did in terms of preparing my quantum state. Then the Bell sampling gives you an advantage over cross-entropy benchmarking, because the purity is an efficient, computationally efficient estimator of the fidelity, as opposed to the cross-entropy. Okay. Awesome. Okay, scalability. Here the question that, among others, Dorit has addressed, starting with Bremner, Montanaro, Shepard in 2017, and then Shungao and Duan, is, okay, now let's say there's constant noise, right? I'm scaling up my system. I'm assuming there's constant local noise after every gate, say. How hard is it to simulate the quantum circuit? Well, of course, if you wait for long enough, if I run my circuit deep enough, everything is going to be uniform and nothing interesting is happening. What's happening in the regime in which the depth is not very large? Can I come up with an algorithm which, the distribution approach is uniform, but it's not quite uniform yet? Can I come up with an algorithm which will be polynomial time in the inverse noise and the number of qubits in the system? And then, yes, there is. There is if you assume anti-concentration of the output distribution. If you have constant depolarizing and local noise after every gate, you can come up with an efficient classical algorithm. What happens in the Bell sampling case? Well, what we did is we just looked at the recent paper of Dorit, Shun, and everyone else, and looked at what happens to this algorithm for the Bell sampling distribution. We went through the proof and tried to get an upper bound on the trace distance of the sampled quantum state in the algorithm. Turns out the upper bound to the trace distance that you get here is exponentially large. So the algorithm seems to be very specific to the choice of computational basis as a measurement. In particular, if you now do a Bell sampling measurement, the best upper bound that we could yet come up with is an exponentially large upper bound for the sample distribution in this algorithm. And there might be reasons for that. The reason might be that if you look at the Bell sampling distribution, actually all Paulis contribute to the distribution. You can't only look at the Z Pauli, say, which at the end of your, for people who don't know about it, just zoom out for a moment, of the end of your path that you're sampling have a Z. Now you actually need to take into account all Paulis, right? Because we saw that the Bell sampling distribution is basically an overlap with Pauli matrices. So you really have to look at all the Paulis. So it might be the case that simulating Bell sampling in the constant noise regime is actually something that's more difficult than computational basis simulation. So is the quantum advantage of Bell sampling more noise robust is the question. Okay, that was it. Let me summarize. So I asked this question whether there's a scalable, verifiable NIST quantum advantage by looking at random circuit sampling experiments and asking whether you can make them verifiable a little bit. And I told you how in Bell sampling you still have hardness of sampling, but then also you have a structured output distribution which has efficient property tests. And I came up with two tentative conjectures. One, that if you add those tests to the cross-entropy benchmarking test, then you might have a more noise-robust quantum advantage. And then, or more difficult to spoof by classical algorithm quantum advantage. And then the other was that maybe the Bell sampling distribution is, maybe Bell sampling is actually more noise robust to constant local noise in the scalability, in terms of the scalability of the advantage than standard basis sampling. I asked you a lot of questions, and I hope that some of you might take the time to look at them. One was, of course, the noise robustness of Bell sampling, the question of hardness of achieving high test scores on those various tests that I gave you. Then there's the question, which I haven't raised yet, but which I think is very interesting, is whether Bell sampling is actually a universal model of quantum computation. So you could think that, I don't know it yet, you could think that maybe now you can encode qubits in the basis rather than just computational basis states, for example. Then there's the question, well, I said there were tests, but I haven't actually written down exactly this is what you should do. So how do you actually make the best possible use of the samples that you get from a Bell sampling experiment for different use cases, say a complexity-theoretic test or an experimental test. Then one question that I think is very interesting, basically coming from this intuition that Bell sampling is intermediate between full fault tolerance and just single copy. What happens if you look at more copies? Actually, back in the 90s sometime, back when fault tolerance was invented, there was a paper which looked at a sort of repetition code for quantum systems, which basically said, well, you take many copies of a system, you project it onto the symmetric subspace, that's going to mitigate some errors. Maybe that sort of idea you can also run here, but now not for computing expectation values on a single copy, but really for the samples from the distribution. And that's all. Thank you very much for your attention.
This reminds me a little bit of the fact that it was shown recently that if you have a single copy of a quantum state and you wish to make a bunch of measurements which will in advance give you the outcome of the product of any Pauli's, that it's exponentially better to have two copies and make Bell measurements.
Right.
And that's shown by just information theory stuff.
Yeah.
So is your thing related to that in any way? It's reminiscent.
It's reminiscent, yes. It's reminiscent, but it's not the same because I'm not sure if I know exactly which work you're talking about, but I think what they do is maybe they do random measurements in entangled copies, or just the Bell measurement.
No, they just take two copies.
They just take two copies.
What they do, I mean, as far as I understand, is you want to make a certain number of measurements, and I'm going to tell you afterwards, I want you to tell me the expected value of a product of Pauli's in that state.
Right.
And you can show that it takes forever if you have one copy.
Right.
If you have two copies, which are just
Right.
unentangled, but then you make Bell measurements with, order n measurements, you get a set of numbers.
Right.
Which allows.
Yeah, that's exactly related to the fact that if you make a Bell measurement, you can compute the outcome of any product of Pauli measurement, right? P tensor P. And then you just need, then you estimate the trace rho P squared, essentially, and then you just make one additional measurement to get the sign, right?
Right. Yeah, that's what they do.
That's exactly the sort of advantage, right? That now you're going into the mixed state picture somehow, right? Yeah. So you're really looking at overlaps between the state and Pauli matrices.
Okay.
So you're like copy and pasting the circuit and then doing a Bell measurement. You could also imagine doing other sorts of stuff, like you can copy and paste the inverse circuit or the complex conjugate circuit. And
you can go crazy, Yeah, I mean, so for example, for this magic test and learning Clifford plus D circuits, if you're able to take the circuit and the complex conjugate, things will become much easier because you don't have the problem.
You're not copying two copies. There's a difference.
Yeah, there's a big difference. And I think this is really what's intrinsic to quantum mechanics, right? The Bell state.
You have to start with two. You can't copy.
Yeah, I just meant like you could.
I know what you meant.
If not, let's take the rest of the questions offline. We'll come back at 2.